Alright, continuing with this series of videos. Yes, watching and commenting on how physics is presented in typical university style lectures, something like that. So, on to the show. I'll go back a little because the video did failed. Yeah. In the last episode, and so I don't know exactly how far we got, so we'll just pretend we got about here or something. Maybe a little further. I think we're on transformer, so get to there. That sort of looks like a transformer there. Close enough.
In terms of eddy currents, very often these two coils are coupled through an iron core, and then you get eddy currents in the iron core, then you lose energy. Also, do you not always have ideal flux coupling? So it is not always true that the magnetic flux through one coil in the primary is the same as the one through one coil in the secondary.
Right, so it just kind of has to be done precisely and such. But I mean, the idea is to to capture. Yeah, really, without the core, it's difficult. Just do it with wires, because the core really helps create the magnetism, which gets out further, and it's getting out further that makes it really easy to capture. So,
but if all of that were the case, so if R is much less than omega L, and if there is no energy loss in eddy currents, and if there is perfect flux coupling, then you can show that whatever power is delivered on the primary side is going to be consumed on the secondary side. And if that is true, if the power delivered on the primary side, which is I1 V1, if that is the same as the power consumed on the secondary.
Yeah, so, it's a small detail, but I wouldn't use the word power consumed, because in a sense you could just be taking the power and putting into a battery or some other device and blah blah blah. So, it's not really transmitting and receiving. It's kind of I think a wrong metaphor.
Side, then that must be I2 V2. But if this is true, which is only under those conditions, and this is also correct, then of course you'll find now that I2 divided by I1 is N1 divided by N2. And let's put here magnitudes again, so that we're not worried about possible minus signs. And when you look at this, you see that you can generate, if you want to, in the secondary, an enormously high current by simply having a large ratio N1 to N2.
Yeah, what you're really doing is transferring the wattage, the power, as he just said. And power is the current times the voltage. So he's just pretending voltage isn't the significant factor when it's hugely important.
And I will demonstrate that today, that indeed, if you meet those conditions, that you can indeed do that. I2 over I1, that's fine. V2 over V1, that's fine. So I will do two demonstrations. The first thing I want to demonstrate is that if I make, oh, that's beautiful. I have to erase something here, or actually I can work on this board here for a while. I have here a demonstration whereby you see here the primary coil. You see it right in front of you. It has 220 windings. So N1 is 220. And V1 is 110 volts, and it is AC, has to be. The frequency is 60 hertz, just what we get out of the plug here, like you get it in your dormitory. That means omega is about 377, it's 2 pi times F.
So it's a lot of watts, but omega he called that, so, it looks like a W. It's only 270 windings. It's got to be a pretty heavy wire then.
If you really did correct value for V1, it's really the maximum value for V1 times the cosine of omega t. And this value is really 110 times the square root of 2. I've mentioned that earlier in my lectures. The voltmeter, however,
I mean, the square root of 2 just doesn't even make any sense to me, but whatever.
designed in such a way that they only show you 110. And so we call that 110 volts. I can now make the secondary just one winding. I have a wire that I wrap around once. And if indeed that equation holds, which it will, I expect now that V2 will be about 0.5 volts. Namely, the 110 volts divided by 220, which is the ratio primary over secondary. And then I will put 4 windings around, and then you expect about 2 volts. And you will see it very right in front of you. This is where you're supposed to see the reading. I can't see it.
So there's, yes, a clear, nice, even one-to-one relationship. I didn't even think it was that clearly a one-to-one relationship. He's basically saying that, yes, each winding contributes to the voltage you get out of, depending on how big the winding is, of course. The initial winding. And that's going to dictate how many volts per loop you get. And then when you're transferring that, there's a clear one-to-one relationship between the number of windings and how much you're going to be able to pull out of it. I don't know how exact it would be, but yes, close relationship.
I have to trust you when you give me those values. Okay, so here is my primary coil, and here is my secondary. This is my secondary coil, and the way I have this demonstration is that this is completely open. So I only show you immediately the value of V2. I'll show you this value. It has a huge value of a resistor, several mega ohms. So for sure, I don't meet this condition. But that condition is not necessary for this to hold. That condition is necessary for this to hold, not for this to hold. So I have no fears that I'm going to be embarrassed. So I'm going to put this is a very long wire, I'm going to put one loop around there. I'm now powering this solenoid. There's an iron core in there. 60.
I wish he would explain where is the coil down here at the bottom? Is it coiled all the way up? Where's the coil start? Where's coil end? Oh, that would be interesting.
Hertz, 110 volts. And there we go. One loop around it. I measure 0.48 volts. That's not bad. Now I put 2, 3, 4 around it. What do I see now? I see 1.99.
Right, and he put them around tight. So he didn't do a loose thing or any kind of other stuff. But anyway, and they're close together, which I think is also going to be semi-necessary. But it might be, it just depends, as long as you're over the coil, the initial coil. So as long as you're over some part of where the wire is actually coiled, it shouldn't matter.
6, you may not see the 6. Very close to 2. What I will do now, I will move it up a little. And when I move it up a little, the secondary, the flux coupling is not ideal anymore. And so you expect that V2 will go down. Just move it up a little along the primary, and you see the value goes down. But now the flux coupling is not ideal.
So it would have been nice if he did show, how this thing is wired. Because obviously, as you get towards the end, as I pointed out, then all the stuff can start escaping. So there's not as much reflecting on the inside. So the maximum amount would be in the middle. Yes. And towards the ends would be less because some of the reflections aren't reflecting, obviously. They're leaving.
And if I bring it further out, flux coupling becomes hopeless, and when I bring it here, the flux coupling...
So that's very, like I said, that's quite consistent with my theory that the whole thing is based on stuff reflecting on the inside.
It's so poor, but I still get 0.3 volts, by the way.
Which is pretty bad when you consider your math is basically not pointing that out anywhere. It's not in your math anywhere that this coil is very sensitive to position.
So that's the first part, to show you that this is indeed quite accurate. Now I want to do a second part, and that is more interesting.
It's only accurate in the middle of the solenoid. Not as soon as you go a little bit away from the edge, it starts becoming inaccurate very quickly. That's what he demonstrated pretty much, right? Didn't have to move it very far to lose a half a volt.
I'm going to try to convince you that I can get a secondary current which is huge, maybe even 1000 amperes. But now I have to take special precautions. I have to do the experiment in a very different way.
All right, so yes, so amps is the current and volts is the voltage and watts is the end result. So you have a certain number of watts going in, and you can change, how those are apportioned. And the higher the current, the harder it is on the wire. The higher the voltage, the easier it is on the wire. But the more likely it is to get sparks across wires. So yes, there's a bunch of interesting trade-offs, if you want to call them that.
And the way I'm going to do this experiment now is with a secondary which is specially designed to have an enormously low value of resistance, because I want to approach this situation so that this approximately holds. We have a very thick copper secondary, almost ½ an inch thick. It's like so. This is copper, and I put here a nail, an iron nail, and the resistance of this iron nail is about 4 times 10 to the minus 4 ohms. The self-inductance of this ring, purely geometry, has nothing to do with the kind of material I have, is easy to estimate. I made a calculation and I found about 5 times 10 to the minus 7 Henry. So omega times L2, I have to multiply this by 3.
Yeah, I don't think it's a great idea to call it self-inductance, but whatever, because I don't think it's doing anything like the traditional coils of wire. The principle is really not the same, but whatever.
377 becomes about 2 times 10 to the minus 4 ohms. Even though R2 is not much smaller than omega L2, they are now beginning to be comparable. My I1, the current that I drive in the primary, is going to be 20 amperes. I do not expect that I2 will be 220 times larger than I1, because I use the same 220 windings for the coil, and this is just one winding. So I have the same ratio N1 over N2 that I had before in that experiment when I did N2 equals 1. I don't expect that this is going to be 220 times 20 amperes, which would be about 4,400 amperes. Because I am really not in the domain that R is much smaller than omega L. But I probably get 500 to 1,000 amperes. And if my current, I2, becomes 500 to 1,000 amperes, you can calculate what I square R2 is. Because you know R2, that's all in that nail.
So this really sort of has to do with the quality of the coupling, and the solid material is solid. Maybe if he had the solid material that actually wrapped around more of the, say if it's made like a horseshoe and it's thick this way, well, if you made it thick this way, you probably would get a higher amperage. See, these are all the details that I wish were, they have time for it, obviously, and I don't know, how physics should be. I mean, these are only hour lectures, the subjects are huge, and you got all this stupid math to do, but it just seems like the experiments are where the truth is gleaned, and it would be interesting to see how it makes a difference, whether that hunk of copper, the same mass of copper of a different shape, a sleeve, would collect more power than one that's thick this way. Being thick this way probably doesn't help it any. Being thick wide doesn't do it any good. Being thick high does it good.
And that comes out to be about 100 to 400 watts. You better believe that nail is going to be red hot, it's going to glow and probably melt. And this is the idea behind so-called induction ovens. This is purposely done to get a very high temperature. It's also done in welding to get very high currents.
So again, I don't know exactly why it's called induction. I mean, obviously it's not self-induction, so I guess that's where we get into the language problem. Yes, it's obviously it's an induced current, so that's true. It's induction, but it's done through a transformer, so it should be given a different word.
And so the second part of the demonstration is the same primary. I want to make it dark so that you can see the glowing of that nail, and I will also show you, of course, first so here is the coil, and here is my secondary. This is that very thick.
All right, so at least we now saw the wires really well. So they're just wires from that thick base going up. So when he did hold it, well, he had them towards the end, but the end has got this big metal thing on it, so that hunk of iron at the base probably helps keep the magnetism from leaking as much, because it's obviously connected to the core, so it goes back into the core through that thick base. So at the bottom there might still be might not be as open as at the other end, which is kind of, so again, it's another piece of the experiment that's a truth. The coil isn't like they draw them same on both ends. This coil has a big hunk of steel at one end, or iron, and nothing at the other end, and that again changes the experiment.
Copper, and then you see the nail here. Make sure there's no current. My God, I almost shoved it over there. Thank goodness that I realized that there was current. So the current is now.
Yes, well, so you can see it's a big thick piece of copper, and if they had made it thinner and taller, it'd probably work even better.
Not going through the solenoid, and so here is the secondary now. Put some pieces of wood under there so that you can see it better. And so now if I power the primary, I can't tell you exactly what the current is through the secondary, but it's probably somewhere in the vicinity between 500 and 1000 amperes. It will glow. It may take 1 minute to melt. It may not melt at all. It may take 3 seconds. Unpredictable, because we don't know exactly the resistance of that.
So, I mean, it really shouldn't be that unpredictable, but whatever.
Nail. So I will tell you when I do it. I will count down. 3, 2, 1, 0. It's already gone. That was fast. So you saw it glowing, and you can actually see that
So they had it under a little bit of tension, so the screws they tied it compressed the copper, so it sprung. So that's why when it made a quick disconnection. So he probably could have let it go. If he had done it loose, then he could have let it, drip.
It melted. So you've seen an example now where the current is immensely high. So now I want to discuss with you another practical application which has immediate consequences, or applications I should say, in your cars. Spark plugs. Cars have coils.
So we did the low voltage example, now we do the high voltage example. I mean, low voltage, high current, high voltage, low current.
And coils are run by a car battery, which is DC, it's not AC. But you've got to get high voltage to get a spark going in, spark plug. And that's done in a very clever way. So here is my 12-volt battery. There's always some resistance, of course, in the circuit. If you have a coil, you always have some finite resistance. And then here is a coil, and here is a switch. And this has N1 windings, has a certain self-inductance, the same situation that we had before. And then I have here a secondary, where I have N2 windings, which is way, way larger than N1. I close the switch, a current is going to build up, and the time constant is L over R, seconds. We discussed that before. It's going to build up. And now we're going to do...
So it's got to be, when he says way more, it's like 10,000 times more. So we're talking 10,000 volts or so for the spark. Something like that. So it would have to be 1,000 times more windings.
Something extremely cruel. I'm going to open this circuit, open the switch. Imagine what I'm doing. I'm cutting instantaneously the current. The current is going happily, reaches a maximum value after several L/R seconds, and now I open it up. So I get a huge value for the I1 dt. I1 is now the current in the primary. The current, of course, will die down on a timescale L/R, which is the new value for R. And the new value for R is the fact that I open it up, I make the resistance infinitely large here. And if the resistance is infinitely large here, my L/R time goes to 0. So that makes you see indeed why the I1 dt becomes enormous. With a 12-volt battery, you can easily get several hundred volts EMF now, because the I1 dt will of course create an EMF, an induced EMF in that circuit, because you get a dphi dt. You get an enormous change in the magnetic flux here, which is directly coupled to the current, and that induced EMF could be several hundred volts. But now look at the secondary.
All right, so the argument's a bit different because it's not AC current, it's DC. So the idea is you initialize the coil, the first coil. It slowly charges up because of that self-inductance. It slows it down. So it takes it a little time because it's building up all these reflections on the inside. So it's filling the battery. The battery's inside the coil. So it's filling the interior of the coil with this reflecting energy. Then you open the switch, and once it's full, or something like that. And when you open the switch, the energy that's inside of that thing isn't going to leak out somewhere else, but the other coil is going to be picking it up. It's going to be yeah, it's going to be picking it up. It's going to be draining it. So it's a good illustration of the fact that this inductance thing doesn't happen by some magic thing. You're actually absorbing a force. So when the force is induced, it's induced because it's being radiated, and it's the radiation of it that So the real point is that when the coil is by itself, just coil with without something ferromagnetic inside of it, it'll hold the charge longer, or it takes longer for it to dissipate than if you have an iron core in it, because the iron core will be creating a lot of the magnetism thing happening. And so it'll always dissipate faster if it has a core in it anyway.
The secondary has an N2 which is way larger than N1. So the induced EMF in the secondary is very rough.
So it's another way of looking at it. The first coils are like a little battery that's loaded over time, and then you're discharging it quickly because it has a core in it. The core is draining it. It's doing the whole EMF thingy, the whole blah 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 eddy current crap that isn't really happening, but anyway, to create the magnetism. So it drains it quickly, and draining it quickly, it's taking something amperage that took a while to put in, a little bit at a time over time, and it's giving it all back at once.
The N2 over N1 times the induced EMF in the primary. That was the ratio that we had earlier. The V2 over V1, remember, was N2 over N1. So now I get in the secondary an absolutely horrendous potential difference. I could get up to 1,000,000 volts if I want to. In your cars, that is not necessary. It is enough in your cars that you get here something like 10 kilovolts. And that will comfortably give you a spark over your spark plug. And so what is happening with your car without you realizing it, there is a circuit that closes and opens and closes and opens and closes and opens. And it's only when you open it that you get this pathetic high voltage here, and that the spark flies over.
Pathetic high voltage. Well, anyway, kind of a funny way to say it. Right. So it's a subtle change in how the experiment's done, And so it's not exactly the inverse of the previous experiment, because that was AC current and this is DC, but it's taking advantage of the fact that when you turn it on and off, you're filling the capacitor, which is also, the coil. The inductor is also, in a sense, a capacitor.
And if you run your engine at 3,000 RPM and you have a 4-cylinder, that happens 200 times per second. But it is the braking that does it. And I can demonstrate this to you. We have a very special spark plug. Maybe it should not be called spark plug. It's a beautiful device. You'll see it all the way over there. And we have there a situation whereby we don't even know what N2 over N1 is. This is an ancient work of art, probably built in the 19th century, or maybe early 20th century. We think that N2 over N1 is at least several thousand, but let's say it is 10 to the third, but it could be way higher than that, we don't know. And we run it with a car battery,
1,000
just like your
times.
car, 12 volts. We let the current build up in the primary, just like we have here, and then in a very cruel way, we open the primary, and we create in the secondary up to 300, 400, 500,000 volts. And then what you will see a spark fly over here.
All right, so I am no expert, but 10 to the third, seems to me that you're supposed to add 3 more zeros, right? So that would be 10,000. So I don't think it'd be 10,000 times more windings. But anyway.
At 300, 400, 500,000 volts, you can draw a spark over a distance of 10 centimeters easily. Because all you have to do is...
Oh, yeah, okay. So, yes, this is a much bigger voltage he's creating. So, okay, so that's why it's 10,000 times the ratio. Because he's making 300,000 volts or whatever.
Get above 3 million volts per meter, which is the breakdown electric field. And this is what I want to show you now. And for that, I also have to make it a little dark, because if you want to see sparks, of course, you want to make it a little dark. So this is the way we are going to do it. Maybe you want to take a look at that beautiful coral first. It's there. So this is the whole setup. Here you see the car battery there, just 12 volts. And here you see the secondary. This is the open end of the secondary, those 2 little balls that I have there. And all of this is enclosed. We cannot measure very much. And so now I will change the lights for you. Okay, I'm now running a current through the primary. And that current is about, oh, we don't even know what the current is. I can't tell you. All I can tell you is now I will open up the current in the primary. So, boy, I didn't mean to kill myself, but I did in the process. Okay, I open up the switch, and every time that I open it, you see there this enormous voltage at the secondary. This is the way that your car coil works, and that you get sparks in your spark plug. That is an enormous potential difference there. We can also set this in such a way that it opens and closes without my having to do it manually. And then you get an idea of how your spark plug works, but that's not the reason why I showed it to you. It's such a wonderful piece of engineering. And a lot of research was done in the early part of the 20th century with instruments like this. It was named after the person who invented this, which is Ruhmkorff. And when I was a student, we always referred to this instrument at the Ruhmkorff. Well, let it go. So when you walk out, you can...
Looks like a Rumpf course, actually, but whatever. Rump.
Come close, but be very careful. You're dealing there with several 100,000 volts. Okay, have a good weekend.
Alrighty then. So that was interesting. Yeah. Subtleties I hadn't considered before, so good. I learned something. Yeah. So I think my explanations are reasonable enough, and so I think I did my job here. So till the next time and such.